right, chapter 2, problem number 12. They're asking for atomic masses to be calculated from the isotope masses in table 2.6. The hardest part about this problem is correctly transcribing the numbers from the table to your paper and from your calculator to your paper. So I've done all that ahead of time to hopefully make sure I didn't make any mistakes. Atomic masses are super important. We're going to use them to calculate molecular masses, the mass of a molecule, by adding up the masses of the atoms that make it up. So they're asking for silicon and calcium, and we did silicon here. 3 isotopes are in the table, 28, 29, 30. This is the mass of each of those isotopes in the unified mass unit. And I think the confusion that someone was asking me about where the decimal point was comes from this idea of abundance. So in the table, it's listed as 92.223, but at the top it says this is a percent. So it's 92%, 0.223. For the calculation, we need to convert that into a decimal number. So percent means over 100, right? Cent is 100. So we're going to take this number 92, etc., put it over 100, which is the same thing as dividing it by 100 and moving the decimal point over 2 places. So that's what I've done here in red. So I took the decimal point, I moved it over 2 places to convert all these numbers into decimals rather than percents, because we can't do math calculations with percents, we can do them with decimals. So you can see this is almost equal to 1. 0.92 is if you round it up to 1. So that's why this number 27.9, when multiplied by a number kind of close to 1 but less than 1, is going to yield a number kind of close to what we started with but less than. And these very small decimal numbers are going to yield very small fractions of 28, 1, and then 0.9. So that's what's going on there. So you're going to multiply the mass times its abundance. You'll get these 3 numbers. You add them up. And now we need to figure out about significant digits. The least precise significant digit is what I have circled here. I used to call it the leftmost place value, but it is the place value with the least precision. And so we're going to round to the thousandth place. And so your final answer will be 28.086. And then we can compare that to this value, silicon, 28.086, which is very close. I think in the book it's 0.855 or something like that. But that points to the fact that these 3 isotopes account for almost all of the silicon in the world that was used to come up with that value in the back of your book. Calcium, same thing, calcium 40, calcium 42. We've got the mass of each of those isotopes multiplied by its abundance, converted into decimal from the percent value. And we get these 2 numbers. This 0 is significant because it's after the decimal point. And we add, and so we keep that decimal place. And here's your answer, 39.001. Now, the value in the periodic table is 40.078. So they're not as close as it was for silicon. And some student, Danny, thank you, asked, why doesn't the abundance of calcium add up to 100%? So that's a good observation. If we're accounting for, all the isotopes, let's say for silicon, you should add up these numbers, 92, 4, and 3, plus the decimal places, and get something very close to 100%. Calcium, not so much. 96 and 0.6, or maybe 97 and 0.6, is not 100%. And the reason is, I looked it up, there are 26 different isotopes of calcium. So in table 2.6, only 2 are listed. So that's why that makes up the difference. There are many other isotopes that didn't make it into the chart that account for the difference to get that up to 100%. All right, and I didn't do the last one. It's the same, and it's also the same as, I think, example 2.1 in your book. All right, bye.